Welcome back, students. In this section, we'll talk more about acid-base balance. We saw how buffers act as the first line of defense, how they can help in buffering a strong acid, whatever acid assault is that is taking place, how bicarbonate is acting as a very good buffer and helps in buffering. But we also saw that buffers cannot eliminate the acid within the body and what to do for this. How can we make up for the alkali reserve? How to eliminate out acid from the body. So as I said, the second line of defense is the respiratory system. How does respiratory system help in maintaining the acid-base balance? So the respiratory regulation of pH, this is mainly for the respiratory system. Main action is eliminate carbon dioxide out from the body. That's the main function throughout carbon dioxide. And what is carbon dioxide? It can combine with water to form carbonic acid. So it is an acid. So thereby we are eliminating the volatile acid out from the body when we are eliminating by the respiratory system. So whenever carbon dioxide is eliminated like this, what will happen? It will be the denominator that is going to be affected. Why? Carbon dioxide is a part of, forms carbonic acid and H2CO3. So it brings about changes in the PCO2 and changes in the denominator as far as pH is concerned, and thereby it starts in regulating the whole pH. The denominator is what is regulated. Now the rate of elimination of carbon dioxide. How much of carbon dioxide is to go out of the body? Depends on what? Depends on the rate of respiration. More you respire, more is the carbon dioxide thrown out of the body. So, and what is this rate of respiration controlled by? It is controlled by the chemoreceptors in the respiratory center. There might be other mechanisms also. Let us focus on the chemoreceptors in the respiratory center. Why? Because they are sensitive to the acid-base balance or to the protons, in other words, or to the carbon dioxide concentration. They are sensitive, the chemoreceptors. So let us look at only the chemoreceptors and how they help in maintaining the acid-base balance. So whenever there is increased carbon dioxide, what happens? The pH decreases. Whenever the carbon dioxide increases, it increases production of acid and the pH is going to decrease. So this is going to stimulate the respiratory center. So it will cause hyperventilation. So minute you have increased carbon dioxide, you will start hyperventilating. So when you hyperventilate, what happens? Again, this is all reversible. It goes in this direction and carbon dioxide gets eliminated out from the body and the pH comes back to normal. So carbon dioxide is washed out and pH is brought back to normal. Now similarly, whenever the carbon dioxide level has gone down, that is, there is decreased carbon dioxide, or it may be the other way around, there is increased bicarbonate or hydroxyl ions also in this case. So if this is increased and this is decreased carbon dioxide has decreased, so the denominator has decreased, what can happen? The pH increases. Carbon dioxide is an acid, so when there is acid is decreased, you call it alkali. The pH has increased. So what? It depresses the respiratory system. What will happen? Hypoventilation. So what? Carbon dioxide is retained in the body and pH is brought back to normal. So this is the role of the respiratory system in maintaining the acid-base balance within the body. Now out of all this, I'll be talking about hemoglobin as a buffer. Now let us look at, I told you hemoglobin is actually a protein which is acting as a buffer, but I want to add some more regarding, since we are talking about the respiratory. Remember, they all are going hand in hand. It is all integrated within the body. Nothing is separately handled. Buffers are not alone. The respiratory system is not alone. They all are happening together. So let us now look at hemoglobin as a buffer. How it is acting as a buffer. Now at the tissue level, what happens? There is high carbon dioxide, isn't it? Where TCA cycle is happening, where muscular exercise is happening, in all these places, the carbon dioxide level has gone up. Metabolism has taken place. So at the tissue level, something should take place to see that what will the hemoglobin do. So there is something called as the Bohr effect. What is this Bohr effect? Now as the pH decreases, the affinity of hemoglobin for oxygen decreases and it leads to unloading of oxygen. So whenever in the tissues, what is happening? This is formed. Okay? Let me just rub out the hydrogen Heisenberg equation. So in the tissues, carbon dioxide is more, carbonic acid is more, protons are more. What will protons do? They will go and bind to hemoglobin. When they bind to HbO2, actually it is carrying the oxyhemoglobin. What will happen? Hemoglobin becomes HHB, that is deoxyhemoglobin plus oxygen, and that oxygen goes to the tissue where it is wanted. Carbon dioxide was there, it has been replaced by oxygen. So this is this shift. At the same time when all this is happening, the oxygen dissociation curve is going to shift, and this is what is going to decrease the affinity of hemoglobin for oxygen and help it unload oxygen. Unloading of oxygen takes place as the pH decreases. Now there is one more thing that is happening in all this, that is called as isohydric transport. Iso means same, and in this case hydric means it means that without any change in pH. How is this possible? Now what is happening is, carbon dioxide is an acid that is being transported in the blood without any change in pH, and this is called as isohydric transport. Say a volatile acid is transported in the blood without any change in pH. How is this possible? The RBCs contain carbonic anhydrates. All that carbon dioxide were combined with water, formed an acid, but that acid is nowhere to be seen in the picture. Oxygen has gone, it is all been, hemoglobin has seen to that, it has buffered everything. All that H plus has been buffered by hemoglobin, and carbon dioxide has been transported as bicarbonate. So an acid is actually being transported as bicarbonate rather than an acid. So there is no change in pH. So a volatile acid is transported with no change in pH. So what are the things that are happening? What is the role of hemoglobin? It binds with protons released from released to form deoxyhemoglobin, HHB, and thereby decreases the PCO2. Remember, the carbon dioxide can have three forms of transport. One is bound to hemoglobin itself, which we call it as carbaminohemoglobin. The other is in the form of bicarbonate, the major component, and the other is the PCO2. So to decrease the PCO2, what happens? All this takes place, and it helps in decreasing the PCO2. PCO2 doesn't change much, and it is able to go from the tissues to the lungs. All this is possible because of this effect of hemoglobin. Now there are other proteins and phosphate buffer also buffer this H plus in the plasma. Not just hemoglobin, including albumin and all other proteins also buffer the protons. And in between all this, there is something called as chloride shift that is happening. This bicarbonate is formed in the RBC. So that bicarbonate is going to go out and chloride is going to enter into the RBC. It is at the tissue level. At the lung level, the opposite of all this is going to take place. The chloride shift is opposite. All these reactions are going to go in the opposite direction, and carbon dioxide is going to be released in the lungs. So let us look at what is happening in the lungs. The reverse takes place, and there is unloading of carbon dioxide. When so much of oxygen is present in the lungs oxygen combined with the deoxyhemoglobin, and it forms HbO2. This is the HbO2, and this goes in the reverse direction. It gives out it's a proton, and that will combine with bicarbonate. Again, a chloride shift has to take place. Carbonic acid and carbon dioxide is going to be eliminated out from the lungs. Unloading of carbon dioxide takes place. So the respiratory system, the second line of defense, what it has done? It can act rapidly to maintain blood pH. So imagine you are exercising, immediately your respiratory system is going to start to act. Why? During exercise, more of carbon dioxide, more of lactic acid is produced. So immediately you start hyperventilating to throw out that carbon dioxide. And what is the buffer doing? It is transporting this carbon dioxide from the tissues to the lungs. What is hemoglobin doing? It is also helping in this transport. All the proteins are helping in its transport. The chemoreceptors are going to get stimulated, and hyperventilation throw out the carbon dioxide. So it acts within minutes too, and it can keep on hyperventilating to some time at least. It eliminates one acid from the body. Carbon dioxide has been eliminated. It contributes to some extent to the alkali reserve of the body. Bicarbonate concentration is contributed by the respiratory system. And the rate of respiration can range from 0 to 15 times normal. Normally how much it is? It will remain. It can go up to 15 times normal. This is a temporary solution. Why? We cannot hyperventilate for long. Hyperventilation cannot proceed indefinitely. So the body needs another mechanism, and plus the respiratory system can take care of only the volatile acids. There is no taking care of the fixed acid. So we need one more mechanism, and that is the renal system. The renal system is the third line of defense. The kidneys will come into play. The Shahenshah of acid-base balance is going to come into play. The renal system. What do the kidneys do? So let us look at the renal system. It maintains acid-base balance by 4 mechanisms. 1. It excretes the H+, the protons. It reabsorbs the bicarbonate. Regeneration of bicarbonate by excretion of titrable acid. Regeneration of bicarbonate by excretion of ammonium ions. Let us see one by one all these 4 mechanisms. So, excretion of protons. How does it take place? Remember, the kidneys are the only route for excretion of acid from the body. So, only route for excretion of H+. Now, where does it take place? It occurs in the proximal convoluted tubule. There is net excretion of H+, absorption of sodium, and generation of bicarbonate. This helps to increase the alkali reserve. The kidneys are also responsible for excretion of fixed acids like lactic acid, keto acids, etc. I'll just show you what are the mechanisms and how the mechanisms take place. We'll show you later. Now, reabsorption of bicarbonate. This is mainly to conserve the base. Bicarbonate is reabsorbed in the PCT. Urine is usually bicarbonate free, and there is no net excretion of protons, and there is no generation of new bicarbonate. It is only and only when the plasma bicarbonate is above 25 milliequivalents per liter, it will start appearing in the urine. Otherwise, the urine is not going to contain any bicarbonate. It is mainly meant for making the urine acidic. Acidic means protons. Somehow or the other throw the acid out from the body. Let us not throw out the bicarbonate. Let us preserve the bicarbonate. The kidney's rule is that preserve the bicarbonate. All the alkali is going to be preserved. There is never any net bicarbonate. All the bicarbonate that is filtered is going to be reabsorbed. Regeneration of bicarbonate is one more way. I'll be showing you schematic diagrams of this. Now, what is happening in this? Just look at it. Excretion of titratable acid. Now, this is a measure of net acid excretion by the kidney. Now, the major titrable acid present in urine is sodium acid phosphate, sodium dihydrogen phosphate. It is also called as sodium dihydrogen phosphate. Also, there is excretion of ammonium ions, and these protons are excreted as ammonium and in the form of ammonium chloride. Glutaminase is an inducible enzyme, and as the pH decreases, glutamine uptake increases. Please remember this. I'll be repeating this again. This is a very effective mechanism for the elimination of acid from the body. Now, let us look at what is happening within the kidneys. So, this is the tubular cell, this is the tubular lumen, and this is the plasma. What is the first thing we need to do is reabsorb bicarbonate. So, bicarbonate has reached the tubular lumen. What happens to it? This will combine with the protons to form carbonic acid. Carbonic acid dissociates into carbon dioxide plus water. Carbon dioxide comes into the tubular cell. It combines with water, forms carbonic acid, which dissociates again. And this is the proton gets recirculated. So, and this bicarbonate enters into the plasma. So, what has happened here? And whenever these exchanges are taking place, we need sodium also. So, with proton, when H plus is going out, sodium comes in. And here by HCO3 is coming out, sodium also is reabsorbed. So, what is happening is, along with sodium reabsorption, all this mechanism has taken place. What has happened here? For every bicarbonate that was filtered, that has been one bicarbonate has been reabsorbed. So it starts with the bicarbonate to be reabsorbed into the plasma. This is reabsorption of bicarbonate. Now the second mechanism I said was along with that, remember, protons have to be excreted out. Now there was just removal of the alkali from the urine, but protons, there was no net excretion of protons by that mechanism. So now let us see how protons are excreted, in what form they are excreted, how are they going to be buffered in the tubular lumen. So regeneration of bicarbonate along with excretion of carbon dioxide. So the tubular cell has carbon dioxide, again it is metabolic, and it forms carbonic acid, bicarbonate and protons. What happens? The protons have gone into the tubular lumen and this has to be excreted out. How? What does it combine with? It combines with phosphate. So this is the phosphate buffer system, HbO4 minus, and forms dihydrogen phosphate. Dihydrogen phosphate will combine with sodium to sodium dihydrogen phosphate, and this is the titratable acidity of the urine. So what has happened here? Protons have been excreted as sodium dihydrogen phosphate. At the same time, one bicarbonate has gone into the plasma. So and always there is an exchange that is taking place of sodium. So for every proton that is excreted as sodium dihydrogen phosphate, one bicarbonate is regenerated in the plasma. So every time one proton is going to be excreted, one bicarbonate is going to be formed into the plasma. So this is regeneration of bicarbonate. The other thing I said was protons have to be excreted at the same time as ammonia has a role in this. So let us look at this. Regeneration of bicarbonate along with excretion of proton, again carbonic acid formation. Now this proton has entered into the tubular lumen. Now the tubular cell has glutamine. Glutamine is acted upon by an enzyme, glutaminase, and it is converted to glutamate. So what will happen? It will release ammonia. It can release further also. Glutamate can be further converted to alpha ketoglutarate, and then also one more molecule of ammonia can be released. This ammonia now enters into the tubular lumen. Minute it enters and it combines with proton, it becomes ammonium. Ammonia is converted to ammonium. Here it can diffuse out. Ammonia can diffuse out. But ammonium cannot diffuse back into the tubular cell. It gets trapped in the tubular lumen. And ammonium combines with chloride to form ammonium chloride, which is excreted out from the urine. So, and at the same time during all this, bicarbonate is regenerated. So for every proton that is excreted as ammonium chloride, there is generation of one bicarbonate ion into the plasma. This is regeneration of a new bicarbonate. What has all this done? It has added to the alkali reserve of the body. At the same time, the protons have been excreted out from the body, and plus, depending upon the acid load, glutaminase is an inducible enzyme. It will convert more and more glutamine to glutamate. So let us, renal system, third line, acts within hours to days, provides permanent solution, prevents loss of bicarbonate from the body, contributes to the alkali reserve, and it is the only route for the excretion of protons from the body, and it has tremendous capacity, especially when it is by excreting ammonium chloride or ammonium ions. So there is one concept called as anion gap. Let us look at it. So normally in the lab, the cations are measured in the lab, which are the sodium, which is 136, potassium, which is 4. So the anions that are measured include chloride 100 and bicarbonate 25. Now if you add up, the numbers don't add up. You know, the amount of anions should be equal to the number of cations. So 136 plus 4 is 140 and this is 125. So there is a gap over there, and this gap is called as the anion gap. So in the plasma, the concentration of cations and anions must be equal to maintain electrical neutrality, and this is not happening. So anion gap is defined as the difference between the total concentration of measured cations. We are not talking of Body is always electrically neutral. Only thing is, in the lab we cannot measure all that. That's the only difference. So the measured cations and that of measured anions. What we measure in the lab, it is a anion gap is got because of the lab, because we cannot measure all those things. Okay, it represents the unmeasured anions in the plasma. And normally anion gap is between 8 to 18 milliequivalents per liter, and anion gap is due to proteins, phosphates, sulfates, urates and organic acid. Anion gap is increased in whenever the proteins are anion gap is increased in whenever the proteins are some problem, phosphates have increased, urates have increased, organic acids like keto acids have increased, lactic acidosis is there, ketoacidosis is there. In those cases, anion gap is increased. So with this we come to the end of how the body has regulated the acid-base balance within the body. The respiratory system, the buffer system, the first line of defense, the respiratory system, the second line of defense, and the kidneys, which are the third line of defense. We also saw about the anion gap, and it is increased whenever the organic acids are increased, like keto acids or lactic acid. So with this we come to the end of acid-base balance within the body. Thank you.